All right, here's the bell work. It's a good bell work. Very pretty. I think it's more pretty when it's done, so there you go. All right, here's our first objective for today. I can calculate theoretical probability and experimental probability. Just take 30 seconds and copy that down, please. So theoretical and experimental probability, hopefully we have at least an idea of what experimental means. Theoretical may be kind of a newer word for us in 7th grade, but theoretical means that, well, it happens in theory, not in actuality, which happens a lot in life. People think that theory is reality, but it's just kind of a prediction. And that's what we use these for. So we say, in theory, based on these things, this is what should happen, okay? And this should be kind of concerning to you, especially when it comes to probabilities, because we tend to say, based on statistics, we create probabilities and then use those probabilities to predict the future, which isn't always the case, unless you were able to force people into doing what you want them to do, which we've talked about several times. And yes, it is definitely possible to do that. Experimental probabilities then are they're probabilities, or I guess predictions, based on something that has already happened. Okay, so an experiment means that, you're doing something, some kind of experiment. Usually you think of science, it doesn't really matter. But you would do that experiment and then kind of expect the same results going forward. And then theoretical, again, is just, we say, hey, this is supposed to happen, and so in the future, we would expect this to happen. And you'll hear people use this all the time. This is actually one of the most important lessons. Like if you use none of the other math in your life, this is one of the important ones because this is how people manipulate other people into thinking a certain way. This is not just a politics kind of thing, by the way. This is advertising kind of thing. If you ever see those advertisements for insurances and laughed at them, you should be wondering, why the crap is an insurance company trying to make me laugh? So if we were to actually do this, we're not going to do it, but if we were to do this one, this would be what we would call experimental probabilities. That's why it's saying it's experimental. We would find those values and then we would say, oh, that was experimental, okay? Now, usually what we would expect without performing the experiment, of course, then it would be theoretical, is for these values to be equal, right? You'd say you'd get, if you tossed it 20 times, you'd expect 10 of those tosses to be heads and 10 of them to be tails. Now, that's theoretical, right? Because we would expect that to happen without actually doing the experiment. But if we did the experiment, of course, those numbers are not always this way. You could say, well, maybe you tossed 8 heads and 12 tails. And you say, well, perhaps that's an unfair coin. I don't think 20 tosses is enough to tell that. But there's actually formulas that we can use to figure out if coins are, or tossed coins are fair or not. Not that I think anyone cares, but that's a different story, okay? But this is an experimental probability if we were to actually do it. But again, the expectation, which that would be more theoretical. But we're going to skip this one. There we go. Probability has standard notation. We write P of G. The P that you see right here stands for, well, probability. When they use just the letter, especially for that activity that we skipped, G would stand for green, like drawing a green tile out of some kind of bag or a hat or something like that. So inside the parentheses, of course, you may see some other type of label. It could be P of red or P of 4, P of dogs and cats. I don't know. But it's something will be in there to help us understand what we are trying to find the probability of. P is probability. Now, while we have not had a function unit yet, which you will go over next year, this is essentially a function notation. It's a probability based on something that we expect to happen, okay? And this is the format we use when we're writing these for both experimental and theoretical probabilities. So you'd say, well, how many times is it actually going to happen divided by how much there actually is, okay? So it's a probability is a part to whole relationship usually. And when you're, like for the example that we skipped right there, you say, well, maybe there's, I forget how many it said, but if there were 24 tiles in a bag, then that's how many possible things you can pull out of the bag. And then for green, I didn't see it, but if it was like 6, then you'd have 6 tiles in the bag. Now that would be theoretical, right? Before you actually perform the experiment, you could make this theoretical observation. But of course that can change based on the experimental. It would have a maximum of 6, but it also changes essentially what the bottom number represents as well, okay? Because then you'd be looking for how many times did you actually try this out and how many times did you get a green tile, okay? So this also means that the top number can never be bigger than the bottom number, and it's rare for them to be equal, because that would indicate some kind of 100% kind of probability, which is rare when we're looking at, well, more than one type of thing that can come out, right? But again, is it possible to manipulate these odds in your favor? Of course it is, depending on what you're looking at. So roll the dice 30 times and record the results. We're not actually going to roll the dice, so we're not actually performing the experiment, which means we're not going to be actually solving for any of the experimental probabilities. However, one thing you'll want to remember on the experimental probabilities, like part A here says, what is the experimental probability of rolling a 1? Since it tells us to roll the dice 30 times, it's always going to be out of 30 like this. And that would be true for B and C and D and E and F and G. Yep, all those would be out of 30, okay? Now, sometimes when you find how many, like if you rolled a 1, let's say that you rolled a 1, I don't know, 10 times, just crazy amount, right? This is more than you'd expect, that's why I say that. But 10 out of 30. Just remember that if you ever get a fraction like this that you can simplify, you should simplify it, all right? So you'd say, well, this could be simplified into 1/3. And sometimes they'll want the decimal, so 0.3 repeating. Usually if they want it as a percent, of course you move the decimal 2 times to the right to make that 33.3%. I wouldn't show the repeating symbol on that. But usually on the homework, usually if it wants you to show a percent that needs to be rounded, it will be rounded to the nearest tenth, usually. So that's some good experimental probability. And again, you may get different values depending on that. So this was just, we were kind of just imaginary with that 10, right? You didn't actually do it. But if you got 10, if you rolled a 1 10 times, that way you'd get it. Okay, now, sometimes you'll see this like on part E, right? It says, hey, look, what's the experimental probability of not rolling a 5? Well, what values can you get that are not 5? In this case, you get 1, 2, 3, 4, 6. That's 5 different types right there. Now, this would, of course, it's still out of 30, but you'd have to, if you perform the experiment, you'd have to count those up, and then your sum would go right here. And then if that can be simplified, you would. Then you could change that into a decimal or a percent, okay? Now, that's all the experimental probabilities. We can find the theoretical probability of rolling a 1. Now, since it's theoretical, we would not use 30 as our denominator because theoretically there's only 6 different outcomes, right? When you roll a dice, you can get 1, 2, 3, 4, 5, or 6. And how many of those numbers are 1? Only one of them is 1 6 right there. Now, I'm not going to go into the decimal or percent changing that because you should know how to do that by now, okay? And we don't have time to go over that too much. Well, what is the theoretical probability of rolling a 5? Well, how many, so again, it's a fraction, but how many numbers are possible to roll when you have the dice in your hand? 6. There's 6 different outcomes that can happen. 1, 2, 3, 4, 5, or 6. How many of those numbers are 5? Just 1. So you're saying that we have the same probability of tossing a 1 as a 5? Yes, that's what we're saying, as long as the dice is considered fair. Are all dice fair? No. How do you get an unfair one? I don't know. Why do you want an unfair one? It's a fair question. So what is, yeah, right? What is the theoretical probability of rolling a 2 or 4? Well, how many outcomes do we have possible? Still 6. So that's our denominator, right? It's always out of how many possible outcomes there are, especially with theoretical. But now we're looking at two different numbers, 2 and 4. That's two different outcomes, so that'd be 2 out of 6. Of course, we would want to simplify this fraction, divide them both by 2 to make this 1/3. So you'd have a third chance of rolling 2 or 4. Well, that's double the chances of rolling a 1 or 5 individually. That's true, because now you just doubled the amount of numbers you just chose. Or L, what's the theoretical probability of not rolling a 5? Okay, so here we go. This is a theoretical, I should be on K actually. Let's go back to K. What is the theoretical probability of rolling 3 or 6? Well, there's still only 6 outcomes. This is 2 of them again. So again, we get a 1/3 right there, 33.3%, or 0.03 repeating. Chance of rolling either of those two numbers. It's the same as those other two because it doesn't matter what the numbers are. The chances or probability that you roll one of these is the same, okay? So what's the probability of not rolling 5? So again, this is theoretical, so we're looking at just the 6 possible outcomes. To not roll a 5 would mean that you could either roll a 1, 2, 3, 4, or 6. That's 5 different values there. 5/6. I don't know what the percent is, and I don't really care right now, but that's the fractional value, theoretically, of what we would expect to roll not a 5. Why would you not want to roll a 5? I don't know. Maybe you're playing Monopoly and you're going to land on jail. Something like that. Good question. So they call that frequency. If you do the experiment, how many times did you roll a 1? That's the number you put here. How many times you roll a 2? That's the number you put here, and so forth. So, yeah, on part E, when it says, what's the sum? Yeah, you'd add the not 5 numbers together, and that'd be your numerator right there. What is the theoretical probability of not rolling a 3? Well, again, there's only 6 possible outcomes total. What's the probability of not a 3? Well, there's 5 numbers there that is not a 3, so it's the same as not rolling a 5. It's just a different value that we're looking at, okay? And again, why would you not want to roll 3? I do this all the time when I play Monopoly, probably more than I should. But yeah, you can calculate these. We'll teach you how to calculate compound probabilities next time. What is the theoretical probability of rolling a number less than 8? Oh, numbers less than 8. Well, what numbers are less than 8? It's actually all the numbers on the dice, right? So theoretically, there's 6 possible outcomes, not 8. But how many of those outcomes are less than 8? All 6 of them were. So that's 6 out of 6. That's 100%.
And that's also the experimental probability.
Yeah, that's a good point. Theoretically, of course, it'd be out of 30 instead, but you'd get 30 outcomes that are less than 8, all of them. Well, what about 7? 7 doesn't matter because it's just asked about being less than 8. That's it. Why would you do that? I don't know. Say, hey, come play our game where if you roll a number less than 8, we give you $10. Don't do that, by the way, but you'd lose a lot of money pretty fast. You're a teacher in a 7th grade math class and you want to create an experiment for your class with red, yellow, and purple marbles in a bag. You want the theoretical probability of drawing a red marble to be 1/4, the theoretical probability of drawing a yellow to be 1/4, and the theoretical probability of drawing a purple to be 1/2. If you want a total of 120 marbles in the bag, how many reds, yellows, and purples would you need in the bag? Well, we need these values that it gives, right? Red there is 1/4. We'll start with red. And the other important value that we're going to need on this one is the 120 total marbles in the bag, okay? So this means that, again, we're looking at this as a fraction. If you were to look at 120 marbles, that's how many total marbles are in the bag. So it's our denominator. We don't know yet how many of those we would need to be red. But we do know that we want this to be the same as 1/4, okay? So they're equivalent fractions. This takes us back to proportional relationships. Which means that we have fractions that are equivalent, okay? So you can scale this up if you'd like. The way that we did it usually was with old-fashioned fish method, because we like fish method, or at least I do. You can scale this one, though. You should be able to. Like if you said 120 divided by 30, boom, you get 4. So that means I'd have to take 1 and multiply it by 30 to go backwards to get, well, 30. Okay? Probably should have done that in red. 30. So how many of the red marbles in the bag would be red? Should be 30 marbles. Hey, don't forget to label this because it is a word problem. 30, we can even put red. 30 red marbles. Now, whether you used scaling the fractions like I did, or cross multiplication, or fish method, you'll get the same answer either way. Okay? Let's go to the yellows on this one. Yellow's 1/4 as well. Now, of course, the proportion sets up this way with still 120 in the bottom. And notice we're comparing the same fraction, which means automatic, it'd be the same. So that'd be 30 yellers as well. Oh, what about purples? Well, purple says it's half the bag, right? Now, I'm going to use a proportion, although some of you probably do not, and that would be okay if you do not, okay? So, let's say, well, there are 120 marbles in the bag. It should be equivalent to the value that it says we want in the bag. 1 out of every 2 marbles should be purple. So, fish method on this one, I guess. We can do fish method. This will work. So that would be 120. Do it purple. So 120 times 1 divided by 4, right? I mean 2. That's 2 right there. 60. That's 60 purple marbles. Now, does this mean if you started drawing marbles from the bag, because this is all theoretical, but if you actually did the experiment and started drawing marbles from the bag, would you get, and you drew 120 times, would you get 60? Of course not. Maybe not. Could you? Yeah, of course you could. But would you get exactly 60? I don't know. Probably not with 120, okay? I can calculate theoretical and experimental probabilities. Hooray! Now, do keep this in mind with theoretical and experimental probabilities. Just like I said right there is, depending on how the questions are worded, will determine the probabilities that happen, right? And is it possible to lead people into certain outcomes? Of course it is, of course. And that's the scary thing, is that it is possible to lead people into certain outcomes with various probabilities. I mean, numbers is one way to do it, because how many people actually question probabilities, right? When you see statistics on the news, or heaven forbid you see them on Twitter or Facebook, I mean, how many of those are legitimate? I don't know. I mean, but you never hear how they get their numbers usually, right? Oh, we interviewed 300 people. Well, there's, 300 million people in the United States, and then they make a determination on 300 people? That's jacked up, man.